The morning of March 17th, 1944, and Captain Robert Johnson drops his P-47 Thunderbolt into a 60-degree dive toward a German rail yard outside Stuttgart. The altimeter unwinds fast. 20,000 feet, 15,000, 10. His airspeed indicator climbs past 400 miles per hour as the target grows in his gun sight. Below him, black puffs of flak begin dotting the sky, the telltale signature of German 88mm guns tracking his descent. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed because tomorrow I've saved something extra special for you. Johnson knows what those black clouds mean. Each burst contains 1,500 steel fragments moving at supersonic speeds, fragments that can shred aluminum, sever control cables, puncture fuel tanks, but he also knows something the German gunners don't. His 7-ton fighter was built to fly through hell itself. He pickles his bombs at 5,000 feet, watches them tumble toward the rail marshalling yard, then pulls hard on the stick. The G-forces slam him into his seat as the Thunderbolt's massive airframe groans under the strain. Altitude bleeds away into speed, and he's diving through the flak barrage itself, punching through clouds of shrapnel at 450 miles per hour. Metal fragments ping against his fuselage like hail on a tin roof. Then he's through. Clear sky ahead. Johnson levels out and checks his gauges. Oil pressure normal. Engine temperature normal. Control surfaces responding. He looks back over his shoulder and counts the holes. 23 punctures in his wings and fuselage. Not a single one hit anything that mattered. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The German gunners who had just fired at Johnson were excellent at their jobs. They'd aimed their predictions correctly, fused their shells perfectly, detonated them in Johnson's flight path exactly as doctrine demanded. By every measure, they'd achieved a direct engagement. But Robert Johnson was flying home to debrief, while somewhere below, those same gunners were already tracking their next target, wondering why the American fighters kept coming back. This wasn't luck. This was engineering that understood war better than the wars themselves understood engineering. The P-47 Thunderbolt had become the aircraft that redefined what survivability meant in combat aviation. While German fighters were being knocked from the sky by single flak bursts, American pilots were flying Thunderbolts home with damage that should have been catastrophic. The question nobody was asking in early 1944 was simple but profound. Why could the P-47 do what killed everything else? The answer lay in decisions made 3 years earlier, on drafting tables, at Republic Aviation in Farmingdale, Long Island, by an engineer who understood that the future of air combat would be written in industrial-age violence delivered at 400 miles per hour through walls of exploding steel. Alexander Kartveli stood in Republic's design office in late 1940 and studied the combat reports flooding back from Europe. The Battle of Britain had proven something terrifying. Modern anti-aircraft defences were getting very good at their job. German flak batteries were shooting down British fighters and bombers with increasing efficiency. Luftwaffe fighters over England were taking horrific casualties from ground fire. The message was clear. If you sent aircraft into defended airspace, they were going to get hit. Most designers responded to this reality by trying to make their fighters more maneuverable, faster, harder to hit. Kartveli did something different. He accepted that his fighter would be hit and designed it to survive the damage. This wasn't romantic thinking. It was cold mathematics. The German 88mm Flak 18, 36, and 37 guns were the most effective anti-aircraft weapons in the world. By 1944, Germany had deployed more than 10,000 of these weapons across occupied Europe. Each gun could fire 15 rounds per minute to an effective ceiling of 26,000 feet. The shells were fused to detonate at specific altitudes, creating clouds of shrapnel that spread across hundreds of cubic meters of airspace. Allied intelligence had calculated the grim statistics. A single 88mm flak burst created approximately 1,500 fragments. Each fragment was a piece of hardened steel, moving at supersonic velocity. If an aircraft flew through the burst zone, multiple impacts were virtually guaranteed. The question wasn't whether a fighter would be hit during ground attack missions. The question was whether it could survive being hit. WWII examined the anatomy of flak damage and discovered a pattern. Most aircraft losses from anti-aircraft fire weren't from catastrophic structural failure. They were from system failures. A coolant line severed, a fuel tank punctured and set afire, a control cable cut, hydraulic fluid drained, engine block cracked. These failures killed aircraft not because the airframe disintegrated, but because critical systems stopped functioning. He realized that survivability wasn't about armor thickness alone. It was about system redundancy, component placement, and choosing the right fundamental architecture. The engine choice mattered more than most designers understood, and WWII chose the Pratt & Whitney R2800 double wasp radial engine for reasons that went far beyond its impressive 2,000 horsepower output. A radial engine is fundamentally different from the liquid-cooled inline engines that powered most fighters of the era. The Rolls-Royce Merlin in the P-51 Mustang, the Daimler-Benz DB6-01 in the Messerschmitt Bf1-09, the Junkers Jumo 213 in the later Focke-Wulf 4190D models all depended on complex cooling systems. Liquid coolant circulated through the engine block, absorbing heat, then flowed to radiators where air cooled the fluid before it cycled back. This system was efficient and allowed for streamlined aircraft design. It was also lethally vulnerable. A single flak fragment through a coolant line meant the entire system would drain within minutes. Without coolant, cylinder temperatures would spike beyond safe limits. Pistons would seize. The engine would destroy itself. Pilots had perhaps 5 minutes from the moment a cooling system was breached to find somewhere to land or bail out. Over enemy territory, 5 minutes was a death sentence. The R2800 radial was different. 18 cylinders arranged in 2 rows, air-cooled by the propeller wash and cowl flaps. No coolant, no radiators, no vulnerable plumbing carrying liquid under pressure throughout the engine compartment. Each cylinder was a separate unit. If one cylinder was destroyed by flak, the other 17 kept running. If 2 cylinders were blown off entirely, 16 remained. Pilots reported flying P-47s home with 3, 4, even 5 cylinders completely missing, the engine running rough, but still producing enough power to stay airborne. Lieutenant Edwin King, of the 357th Fighter Group, landed at Pisa, Italy in January 1945 with a ruptured oil line and 2 cylinders destroyed by ground fire. The maintenance crew counted 38 flak holes in his aircraft. The R2800 had continued running for 45 minutes after being hit, long enough to get King across the lines and onto a friendly runway. In a liquid-cooled fighter, that same damage would have ended the mission in minutes, probably over German-held territory. But WWII didn't stop at engine selection. He positioned that massive radial engine as a shield. The R2800 weighed over 2,200 pounds. Sitting at the nose of the aircraft, it formed a wall of cast iron and steel between the pilot and frontal threats. Flak bursts ahead of the P-47 had to penetrate that engine mass to reach the cockpit. Most fragments never made it through. Behind the engine, WWII installed the turbo supercharger system in the rear fuselage. This created natural segmentation. The engine compartment was separated from the fuel tanks, which were separated from the turbo supercharger, which was separated from the tail. A flak burst might damage one section without compromising others. Compare this to the German Focke-Wulf Fa-190A series. The Fa-190 was a superb fighter, fast and maneuverable with heavy armament. Its BMW 801 radial engine gave it good survivability against small arms fire. But Kurt Tank's design team had made a critical compromise. The oil cooler for the BMW 801 was mounted in an annular ring at the front of the cowling, integrated into the propeller spinner assembly. This design was aerodynamically efficient and helped solve the FW-190's early overheating problems. It was also an Achilles heel. That oil cooler sat in the most exposed position on the entire aircraft. Any frontal hit, whether from a fighter's guns or a flak fragment, stood a good chance of puncturing it. Once the oil cooler was breached, the engine would overheat within minutes. The BMW 801 required oil not just for lubrication but for cooling. Lose the oil system and you lost the engine. German pilots knew this vulnerability intimately. Luftwaffe combat reports from 1944 and 1945 contain repeated references to oil cooler damage, forcing emergency landings. A single 20mm shell, a single larger flak fragment hitting the nose, and the mission was over. The pilot had minutes to find a field or bail out. In the chaotic, low-altitude environment of ground attack missions, minutes were rarely enough. The contrast became stark during the Allied advance across France after D-Day. Both P-47s and FW-190Fs, the ground attack variant of the Fokker-Wulf, were flying similar missions, attacking German columns, rail yards, bridges under heavy flak defences. The loss rates told the story. Records from the 9th Air Force, which flew most of the American tactical fighter bomber missions in Europe, showed that P-47s were returning from missions with battle damage at rates the Luftwaffe couldn't match. The statistics were brutal. Between June and December 1944, 9th Air Force P-47 units flew over 150,000 ground attack sorties. They lost approximately 900 aircraft to all causes, including flak, small arms fire, and operational accidents. That's a loss rate of 0.6% per sortie. More importantly, of the P-47s hit by flak, roughly 65% made it back to base or friendly territory. The aircraft could absorb damage and keep flying. Compare this to Luftwaffe ground attack units flying the 4-190F and G models. German records are incomplete, but captured Luftwaffe strength reports from late 1944 show that Schlachtgeschwader, ground attack wings, were experiencing unsustainable attrition rates. Some units reported losing 30 to 40% of their aircraft strength in a single month of operations. The WWII was being shot down not because it was poorly designed, but because it was flying into the same flak environment that P-47s were surviving. The difference wasn't pilot skill or luck, it was engineering philosophy. Republic had designed the P-47, assuming it would be hit and built systems to survive damage. Fokker-Wulf had designed the Fokker W190 for maximum performance, accepting vulnerabilities as the price of efficiency. Kartvelli's obsession with survivability extended to every system. The P-47's fuel system was a masterpiece of defensive engineering. The main fuel tanks sat in the fuselage, forward of the cockpit and behind the engine, protected by armor plate on multiple sides. But protection wasn't enough. Kartvelli specified self-sealing fuel tanks, a technology that was relatively new in 1940. Self-sealing tanks used a layered construction. The inner layer was a rubberized material that would swell and seal when exposed to fuel. If a projectile or fragment punctured the tank, fuel would seep into the sealing layer, causing it to expand and plug the hole within seconds. This prevented fuel from spraying into the engine compartment where it could ignite. It prevented fuel from draining out, leaving the pilot with no way home. And it prevented the catastrophic fires that killed so many fighter pilots when incendiary rounds hit their tanks. The fuel system in the P-47 had redundancy built in. Multiple tanks, check valves, cross-feed lines. If one tank was punctured and the self-sealing failed, pilots could switch to another tank and continue flying. If the engine-driven fuel pump was damaged, an auxiliary backup pump could maintain pressure. Every critical system had a backup or a workaround. This redundancy added weight and complexity, but it saved lives. German fighters typically had less system redundancy. The W190 had self-sealing tanks, but they were smaller, and the fuel system was more centralized. A single, well-placed hit could disable fuel flow completely. The Bf-109 had even less redundancy. Its fuel tanks sat directly behind the pilot with minimal protection, and its cooling system was extremely vulnerable to damage. Preparing and narrating this story took us a lot of time, so if you are enjoying it, subscribe to our channel. It means a lot to us. Now back to the story. Armor protection in the P-47 followed the same philosophy. Most fighters in World War II, including German types, had a steel plate behind the pilot's seat to protect against attacks from behind. The P-47 had that, a thick steel plate that would stop rifle-caliber rounds and small fragments. But WWII went further. The cockpit sides had additional armor, the floor had ballistic protection, the windscreen incorporated bullet-resistant glass, even the headrest had armor. A P-47 pilot sat inside what was effectively an armored capsule. When Lieutenant Robert Johnson famously survived a brutal attack by a Focke-Wulf 190 in June 1943, the armor saved his life. His aircraft took multiple 20mm cannon hits. The armor plate behind his seat was dented and cracked but held. Johnson flew home. The structural design of the P-47's airframe added another layer of survivability. Republic used heavy-gauge aluminum throughout the primary structure. The wing spars were thick and strong. The fuselage frames were robust. This wasn't elegant, lightweight design. It was brute force engineering that prioritized strength over weight savings. When flak hit the P-47's wing, it might puncture the skin and damage internal structure, but the wing rarely failed catastrophically. The heavy spars could absorb damage and maintain structural integrity. Control cables were routed with protection and redundancy. If one cable was severed, pilots often had enough control authority remaining to keep flying. By contrast, lighter fighters with thinner skins and minimal structural margins were more vulnerable to catastrophic failure when hit. A single large fragment could sever a spar or critical structural member, leading to immediate loss of control. The P-47's extra weight, so often criticized for hurting maneuverability, was buying pilots the ability to survive hits that would first set down other aircraft. The Germans understood what they were facing. Luftwaffe intelligence reports from 1944 noted with frustration that American fighters, particularly the P-47, were proving extremely difficult to shoot down with flak. One report from August 1944, captured after the war, stated that American escort fighters equipped with radial engines demonstrate remarkable resistance to ground fire. Hits that would disable our fighters often cause no apparent damage. It is recommended that flak batteries concentrate fire to achieve multiple hits on single targets rather than distributing fire across formations. That recommendation revealed the problem. German flak batteries had always been lethal, but they were optimized for bombers flying predictable patterns at steady altitudes. Fighter bombers like the P-47 dove in at high speed, attacked, and were gone before the guns could concentrate fire effectively. Even when they achieved hits, those hits often didn't bring the aircraft down. The frustration was mutual. German ground forces learned to fear the sight of P-47s circling overhead. The American fighters operated in what the Army Air Forces called cab rank formations, stacking up above the battlefield and waiting for forward air controllers to call them down on targets. When the call came, Thunderbolts would roll into their attacks, diving through flak to deliver bombs, rockets, and machine gun fire on German positions. The ground attack pilots developed tactics specifically designed to survive the flak environment. They understood the German 88mm guns had effective engagement envelopes. Below 2,000 feet, the guns couldn't track targets fast enough to achieve accurate firing solutions. Above 12,000 feet, fighters were relatively safe from light and medium flak. The danger zone was between 3,000 and 8,000 feet, where medium flak could track and engage effectively. P-47 pilots learned to stay high until the final attack approach. They would orbit at 12 to 15,000 feet, spot their targets, then roll into steep dives that accelerated them quickly through the danger zone. By the time flak gunners reacted and fired, the Thunderbolts were already below 3,000 feet, moving too fast to track effectively. The pilots would pull out of their dives at extremely low altitude, below 500 feet, where only small arms fire could reach them. They'd deliver their ordnance, then pull up into a climbing turn that got them out of small arms range as quickly as possible and back to altitude where they could either re-attack or head home. This dive and zoom tactic inherited from the high-altitude air combat doctrine that Hub Zemke had developed for the 56th Fighter Group, worked brilliantly against Flak. The P-47's weight, so problematic in turning dogfights, became an asset in vertical maneuvers. The 7-ton fighter accelerated in dives like a falling anvil. Flak gunners trying to lead the target found their firing solutions useless as the Thunderbolt's speed increased far faster than lighter fighters. The pullout from these dives subjected the airframe to tremendous G-forces, sometimes exceeding 7 Gs. The P-47's robust structure could handle it. Republic had over-engineered the airframe specifically to handle high-G maneuvers and high-speed dives. Pilots reported pulling so hard that they blacked out momentarily from the G-forces, but the aircraft never failed structurally. This gave them confidence to push their attacks deeper, to pull out later, to take risks that pilots in lighter fighters couldn't afford. The combination of survivable engineering and aggressive tactics transformed ground attack operations in 1944. Before D-Day, Allied tactical air forces had been cautious about flying into heavily defended areas. Losses to Flak were considered acceptable only if the target was critically important. The P-47 changed that calculation. With loss rates below 1% per sortie, even in heavy Flak environments, commanders could authorize attacks on targets that previously would have been considered too dangerous. This expanded the scope of what air power could accomplish. Railroad marshalling yards, previously protected by concentrated Flak batteries, became viable targets. Bridge approaches defended by mobile Flak units could be attacked repeatedly. German armoured columns moving in daylight learned that no amount of anti-aircraft protection would keep the Thunderbolts away. If the target was important enough, American pilots would fly through whatever defences the Germans erected, deliver their ordnance, and most of them would fly home to rearm and come back. The psychological impact on German ground forces was profound. They knew the Flak was firing. They could see the black clouds of 88mm bursts filling the sky. They could hear the impacts as fragments hit American aircraft. But the Thunderbolts kept coming anyway, dropping through the Flak barriers like they were flying through weather rather than exploding steel. The apparent invulnerability of the P-47 to Flak became a myth that spread through German frontline units. It wasn't entirely accurate, of course. P-47s were being hit and damaged, sometimes badly. But the myth contained a truth. These aircraft could survive damage that killed everything else the Germans had fought against. The mythology of P-47 invulnerability found its ultimate test in the skies over Germany during the winter of 1944–45. The Luftwaffe had concentrated its remaining Flak resources around key industrial targets and transportation hubs. By January 1945, Germany had deployed over 21,000 anti-aircraft guns of all calibers across the Reich. Nearly a quarter of all German war production was devoted to anti-aircraft weaponry. It was the most intensive air defense network ever created. Into this steel-filled sky flew thousands of Allied fighters and bombers daily, and the statistics told a story that shocked even the Allied commanders who had ordered the missions. Between December 1942 and June 1944, the Luftwaffe estimated it had damaged over 20,000 US aircraft with Flak. American records put the actual number higher, over 26,000 damaged. Yet the bombers kept flying, the fighters kept escorting, and the ground attack missions never stopped. The German guns were firing tens of thousands of shells daily. Intelligence estimates suggested that in 1944 alone, German Flak accounted for approximately 1/3 of all Allied aircraft shot down and 2/3 of all aircraft damaged. The 88mm guns were particularly effective, but effectiveness is relative. The Germans were expending an average of 16,000 88mm rounds for every heavy bomber destroyed. For fighters, which were smaller, faster, and harder to hit, the expenditure was even higher. This is where the P-47's engineering paid its most significant dividend. The aircraft could be hit repeatedly and continue flying. Maintenance records from 9th Air Force P-47 groups in France during autumn 1944 reveal the extent of battle damage these aircraft absorbed. Typical entries read like inventories of destruction. 43 flak holes in wings and fuselage, starboard aileron control cable severed, fuel tank punctured with self-sealing functional, 2 cylinders damaged, oil cooler dented, aircraft returned to service after 3 days maintenance. Compare this to German fighter losses from the same period. Luftwaffe loss reports, captured after the war, show a different pattern. Aircraft damaged by flak rarely returned to base. The most common entries describe aircraft last seen trailing smoke, losing altitude, pilot bailing out. The Fold 190, despite its radial engine and relative ruggedness compared to the Bf-109, simply couldn't absorb the volume of damage that P-47s routinely survived. Part of this disparity came from operational circumstances. By late 1944, German pilots were increasingly inexperienced, with minimal training hours compared to their Allied opponents. They were also flying with chronic fuel shortages, often landing with nearly empty tanks and no reserves for emergencies. When a flak fragment damaged an FW-190's engine or fuel system, the pilot had no margin for error. He had to land immediately or bail out. There was no fuel reserve to limp home. There was no nearby friendly airfield where he could make an emergency landing. American pilots flying from bases in France or Belgium had advantages beyond their aircraft's engineering. They had fuel reserves. They had proximity to friendly territory. If a P-47 was badly damaged, the pilot could often glide or fly on reduced power to Allied lines. Ground crews would recover the aircraft, patch the damage, and return it to service. The Germans had no such luxury. Even minor damage often meant the aircraft was lost permanently, but the engineering differences remained fundamental. The P-47's systems kept working when damaged. The R-2800 engine kept running with cylinders destroyed. The self-sealing fuel tanks prevented fires. The robust airframe maintained structural integrity. The redundant control systems gave pilots options when primary systems failed. This wasn't luck or superior logistics. This was the result of design decisions made 3 years earlier by an engineer who understood that survivability was measurable and could be engineered. If you find this story engaging, please take a moment to subscribe and enable notifications. Helps us continue producing in-depth content like this. Lieutenant Francis Gabreski learned these lessons personally in July 1943 when his turbo supercharger took a direct hit from a Messerschmitt Bf-109's 20mm cannon during a high-altitude engagement. The turbine, spinning at 21,000 RPM, disintegrated. Exhaust pressure spiked throughout the ducting system. The engine lost manifold pressure and began running rough. At 28,000 feet, most engines would have quit entirely. The R-2800 kept running. Gabreski descended rapidly, trading altitude for the denser air that his damaged engine needed. At 15,000 feet, the engine smoothed out. It was running on supercharged boost alone without the turbo, producing maybe 60% of normal power. But 60% was enough. Gabreski outmaneuvered the Bf-109 in the descent, the German pilot apparently assuming the damaged Thunderbolt would be easy. Prey. He was wrong. Gabreski turned inside him, fired a burst that hit the Messerschmitt's coolant system, and watched the German fighter trail white vapor as it dove away trailing coolant. Gabreski flew home on the damaged engine. Maintenance crews found the turbo supercharger housing cracked and deformed, the turbine wheel destroyed, the exhaust ducting blown open in 3 places. In most fighters, this damage would have ended the flight within minutes. The P-47 had brought Gabreski home, and after 3 days of repair work, brought another pilot back into combat. The turbo supercharger system itself, so complex and so heavy, contributed to survivability in ways Kartveli probably hadn't anticipated. The system was segmented throughout the fuselage: exhaust ducting, intercooler, oil lines, regulators, wastegate controls. Each component was isolated from the others by firewalls and structural frames. A hit that damaged one component rarely cascaded to destroy others. Pilots reported flying with damaged intercoolers, with turbo supercharger failures, with exhaust leaks, and the aircraft continued functioning. Performance degraded, certainly, but degraded performance was infinitely better than no performance at all. The German Bf-109G, by contrast, relied heavily on its Daimler-Benz DB605 engine's mechanical supercharger. The entire supercharger system was mounted directly on the engine, integrated into a compact and efficient package. Efficient, yes. Survivable, no. A single hit to the supercharger installation could disable the entire engine. There was no redundancy, no backup, no way to continue operating. The pilot's options were to land immediately or bail out. This became a critical factor during low-altitude ground attack missions, where both flak and small arms fire were threats. The P-47 could take multiple hits and keep flying. German fighters took 1 or 2 hits in the wrong places and went down. The attrition, mathematics were brutal. Germany was losing fighters and pilots at rates that couldn't be sustained. The Luftwaffe was bleeding to death, not from lack of courage or skill, but from aircraft that couldn't absorb damage and continue fighting. By the time Allied forces crossed the Rhine in March 1945, German ground commanders openly admitted that air superiority belonged entirely to the Allies. The Luftwaffe made occasional appearances, but increasingly the burden of air defense fell to the flak batteries. And those batteries, no matter how many shells they fired, couldn't stop the P-47s. The 9th Air Force's tactical air operations in the final months of the war became exercises in sustained violence. P-47 groups flew multiple sorties per day, every day, weather permitting. They attacked everything that moved: railroad trains, truck convoys, armored columns, airfields, bridges, ammunition dumps. German forces learned that daylight movement was suicide. The Thunderbolts would find them, and no amount of flak would keep the attacks from coming. Operation Varsity, the airborne assault across the Rhine on March 24, 1945, demonstrated the transformation that the P-47 had enabled. British 12th Corps attempted the largest suppression of enemy air defences mission in history. They fired 24,000 artillery shells in 22 minutes at German flak positions to support the airborne drop. Despite this massive bombardment, German flak guns survived and engaged Allied aircraft. P-47 groups from the 9th Air Force flew direct attacks on the flak batteries before, during, and after the airborne assault. They dove through the remaining flak fire to bomb and strafe the gun positions. Losses were light. The German guns fired thousands of rounds. Many Thunderbolts were hit, but most of those hit aircraft flew home, were repaired, and returned to combat within days. The contrast with earlier, airborne operations was stark. During Operation Market Garden in September 1944, German flak had savaged the transport aircraft carrying paratroopers. The slow, vulnerable C-47s had been sitting targets. But the 1944 operation had proven something. P-47s flying suppression missions against flak could reduce the threat significantly, even if they couldn't eliminate it entirely. By March 1945, the doctrine had matured. Fighter bombers attacked flak positions as a matter of routine before any major air operation. The 56th Fighter Group, Hub Zemke's unit that had pioneered high-altitude dive tactics against German fighters, had by 1945 become expert at anti-flak operations. They developed specific tactics for attacking 88mm batteries. The approach was calculated and brutal. 4-ship flights would attack from multiple directions simultaneously. One flight would make the primary attack, from high altitude, diving through the flak to bomb the gun positions. While the German guns were tracking that threat, a second flight would come in from a different direction at low altitude, strafing the crews. A third flight would orbit high, ready to attack any guns that survived the initial passes. This multi-axis attack overwhelmed the German defensive doctrine, which assumed attacks would come from a predictable direction. The 88mm guns were deadly if they could track and lead their targets, but when multiple targets attacked from different altitudes and directions simultaneously, the fire control became impossible. Gun crews could engage one threat while being destroyed by another. The P-47 made these tactics possible because the aircraft could survive the engagement long enough to deliver ordnance. Lighter, less survivable fighters couldn't sustain the losses that multi-axis attacks incurred. but when your loss rate is below 1% per sortie, even in heavy flak, you can afford to press attacks that would be suicidal in other aircraft. The Germans had no counter to this combination of survivable engineering and aggressive tactics. German industry tried to respond. By early 1945, they were producing improved flak ammunition with better fragmentation patterns. They developed proximity fuses that didn't require accurate range prediction. They increased the density of flak batteries around critical targets. None of it mattered. The engineering decisions Alexander Kartveli had made in 1940 had created an aircraft that could absorb punishment the Germans couldn't inflict in lethal quantities. The final accounting came after the war. Of 15,683 P-47s built, only 3,499 were lost to all causes in combat. That's a loss rate of roughly 22% across the entire war. For an aircraft that flew over 500,000 combat sorties, more than half of them ground attack missions into defended airspace, that loss rate was extraordinary. The P-47 had a survivability rate that no other tactical fighter of the war could match. Individual pilot accounts reinforced the statistics. Lieutenant Leslie Bowes of the 365th Fighter Squadron, 358th Fighter Group, walked away from 4 destroyed P-47s during his 107 combat missions. Each time, battle damage forced him to crash land or belly land the aircraft. Each time, the robust airframe protected him during the crash. He credited the Thunderbolt's rugged construction for his survival. "This plane deserves greater recognition," Bowes said after the war. "I'd fly into any flak with confidence that even if I got hit, I could probably bring it home." That confidence changed how tactical air power was employed. Before the P-47 proved its survivability, commanders were cautious about sending fighters into heavy flak. Losses were considered acceptable only for the most critical targets. The Thunderbolt inverted that equation. Targets that would have been considered too dangerous became routine. Railroad marshalling yards, bridge complexes, troop concentrations, all became viable targets because the P-47 could survive the defences. This transformation accelerated the Allied advance across Europe. German forces couldn't move during daylight. They couldn't supply their frontline units. They couldn't concentrate forces without being spotted and attacked. The operational mobility that had made Blitzkrieg possible in 1940 was denied to Germany in 1944 and 45 because Allied tactical air power could strike anywhere, anytime, with acceptable losses. The Luftwaffe understood what had happened but couldn't counter it. One captured German intelligence assessment from April 1945 stated bluntly, "American fighter bombers, particularly the first P-47 type, have achieved air superiority over the battlefield that cannot be contested by our remaining forces. Their combination of firepower, bomb load, and resistance to flak damage makes them the dominant factor in the tactical air environment. Our ground forces report feeling helpless against repeated attacks that our flak batteries cannot prevent." That helplessness was the ultimate victory of engineering over tactics. The German flak arm had been excellent, their guns were accurate, their crews were trained, their doctrine was sound, but they were fighting aircraft that had been designed from the beginning to survive their fire. The P-47 didn't avoid the flak. It flew through the flak, absorbed the damage, and kept fighting. The engineering legacy of this achievement extended far beyond World War II. Post-war aircraft design incorporated many of the lessons learned from P-47 survivability. The U.S. Air Force's Arten Thunderbolt II, named explicitly honor of the P-47, was designed with the same philosophy. Redundant systems, armored cockpit, engines positioned to shield critical components, ability to fly with severe battle damage. The Arten could survive hits from 23mm and 37mm anti-aircraft fire that would destroy other aircraft. This wasn't coincidence. It was the direct application of principles proven by the P-47 30 years earlier. Modern fighters, even with advanced materials and electronics, still incorporate survivability engineering that traces back to Kartveli's work. Hydraulic system redundancy, multiple flight control backups, armored avionics bays, self-sealing fuel systems, all descended from design features pioneered on the Thunderbolt. The recognition that aircraft operating in defended airspace will be hit, and therefore must be designed to survive hits, became fundamental doctrine for military aviation. The P-47's story also influenced how military planners thought about the relationship between technology and tactics. The aircraft proved that survivability could be engineered, that accepting extra weight and complexity in exchange for damage tolerance was a valid design trade-off. This challenged the prevailing wisdom that fighters had to be as light and nimble as possible. Sometimes, the best fighter wasn't the one that could avoid being hit. Sometimes it was the one that could take the hit and keep fighting. German engineers after the war admitted they had made different choices that led to different outcomes. Kurt Tank, designer of the Focke-Wulf 190, told Allied interrogators that German design philosophy had prioritized performance over survivability. "We believed that speed and maneuverability would keep our aircraft alive," Tank said. "The Americans believed that their aircraft would be hit and designed them to survive." In retrospect, the American approach was correct for the type of war that developed. That admission validated everything Alexander Kartveli had built into the P-47's design. The weight, the complexity, the apparent inelegance of the design all served a purpose. The 7-ton fighter looked like a flying bathtub, but it brought its pilots home through defenses that killed everything else. Beauty in aviation, Kartveli had proven, wasn't about streamlined curves or minimalist design. Beauty was about engineering that understood war and built accordingly. By May 1945, when Germany surrendered, the P-47 had flown more combat sorties than any other American fighter. It had destroyed more ground targets than any other aircraft type in the Allied inventory. 86,000 railroad cars, 9,000 locomotives, 6,000 armoured vehicles, 68,000 trucks. The numbers were staggering, and they represented a transformation in warfare. For the first time, ground forces had learned they were vulnerable from the air even when protected by the most intensive anti-aircraft defences ever created. The P-47 had proven that tactical air power could dominate the battlefield if the aircraft were engineered to survive the defences. This lesson would shape military aviation for the next 80 years and counting. The German gunners who fired at Robert Johnson that March morning in 1944 had done everything right. They'd tracked accurately, fused correctly, achieved hits. By every measure, they'd done their job. But Johnson flew home with 23 holes in his aircraft because an engineer in Farmingdale, New York, had understood something fundamental about modern war. Survivability wasn't about not getting hit. Survivability was about what happened after you got hit. And the P-47, ugly, heavy, unelegant, had been designed from the first rivet to survive what killed everything else. The flak clouds over Germany and France would eventually fade. The 88mm guns would fall silent. The war would end. But the lesson remained. In aerial combat over defended territory, engineering for survivability mattered more than elegant design or minimal weight. The P-47 had proven it conclusively. Written in the statistics of aircraft that came home when they shouldn't have, pilots who survived when the odds said they wouldn't, and missions accomplished despite defences designed to make them impossible. Alexander Kartveli never claimed his design was beautiful. He claimed it would bring pilots home. History proved him right. The P-47 Thunderbolt flew through flak that destroyed German fighters because it was designed to survive, built to absorb punishment, and operated by pilots who understood that their aircraft gave them capabilities no one else possessed. That combination changed warfare, and it all started with an engineer who refused to accept that fighters had to be fragile to be effective. Up next, you've got 2 more standout stories, marks right on your screen. If this one hit the mark, you won't want to pass these up. Just click and check them out. And don't forget to subscribe and turn on the notification bell so you don't miss any upload from us.